Hello, my name is Dongmin Han, a PhD student at Utah State University. I'm glad to present our work on behalf of my co-authors. POTR is an abbreviation of Porter Widget for Remote Target Acquisition and Control. As its full name indicates, POTR is designed for users to select and manipulate distant objects. Motor space and control space are the fundamental concepts to understand object manipulation in VR. Motor space is the physical space available for the users to operate input devices. Usually it is the arm reach distance. Control space refers to the spatial range where the user is able to control objects by using virtual cursors in VR. Then, control and display ratio is defined by delta small x divided by delta large x. When CD ratio is 1, users can only interact with virtual objects within arm reach, as control space has the same range to the motor space. However, if the CD ratio is less than 1, users can interact with out-of-reach objects because the virtual cursors can move beyond the limit of the motor space. Early studies have introduced different types of techniques for remote object manipulation. The first group is direct manipulation, controlling the CD ratio, like go-go, linear offset techniques, and direct homer. The second group is indirect manipulation approaches. Word in miniature and voodoo dolls are the famous techniques for this group. The third method is interacting with a remote object after moving to the remote position. Teleportation is the widely used navigation technique. The secondary view is an additional view that displays a different perspective than the user's primary view. It provides additional interactions for the users. For example, the magic lens technique reveals hidden information when it is overlaid on part of the primary view. The mirror metaphors provide a view in a different perspective by using mirror reflection. To our best knowledge, tunnel window is the most similar technique to Portal, allowing users to manipulate distant objects within a tunnel. The technique is proposed for the cave environment. However, their work did not provide its evaluation compared to the other distant object manipulation techniques. The aforementioned techniques have limitations in terms of providing precise control and depth perception to distant objects. Here are the three design considerations for the porter. First, control space should reach remote objects. Second, precise depth perception. Third, no offset for fine-grained controls to the remote objects. Porter achieves these considerations by utilizing a secondary view. Porter uses the ray casting technique as its selection tool. When a user clicks the trackpad button on the controller, a ray emerges from the virtual hand. When the user clicks the trigger button, while the ray is pointing to the remote target, Porter is created. Porter consists of three elements: primary Porter, secondary Porter, and Porter camera. When Porter is created, the primary Porter is located in front of the user with the distance in the half length of the user's arm reach. The secondary Porter and the Porter camera are created in front of the remote target by a quarter and three-quarters of the user's arm reach in the opposite ray direction. Their orientations are perpendicular to the ray. Once the Porter camera is located in the scene, it begins rendering its view on the primary Porter. Its view is transitioned by plus or minus 3 cm considering binocular disparity. The transitioned images are mapped to the left eye or right eye texture on the primary Porter to make a stereoscopic image. This is the outcome. As a result, the user gets an illusion that the target object is located in three-quarters of the user's arm reach ahead. The user can put his or her hand into the Porter and interact with the distant object. The study 1 designed to evaluate Porter on remote object selection and manipulation tasks. To evaluate its performance, we conducted a comparative study with direct homer and linear offset technique. Direct homer is a hybrid technique of ray casting and the virtual hand metaphor. It uses ray casting to select remote objects. When the user selects a remote object which the ray hits, a virtual hand that shoots the ray moves to the target instantly. The transition movements of the input device is applied to the virtual hand by CD ratio. The CD ratio is dynamically determined by following the distance between the user and a target object. while the CD ratio for rotation is 1. The linear offset technique has a static CD ratio. In this study, the CD ratio is controlled for users to reach a wall from the center in the scene. It was a 1-hour study, and a total of 21 participants were recruited. We used a Vive Pro 1 VR device and its controllers with a wireless adapter. Study 1 includes 2 tasks, selection and docking tasks. Selection task is a multidirectional tapping task with a circular arrangement of targets following the physical task. The docking task consists of 2 tetrahedron objects. The participants are asked to reposition the opaque object to the position of the semi-transparent object. Its position and orientations are randomly decided. They have 2 independent variables, technique and distance, to the task object. The dependent variables are selection or docking time, throughput, number of error clicks or error distance, and task load assessment score. We set 3 hypotheses. First, the further away the target objects are, Porter is expected to have a faster target selection or docking completion time than Homer and linear offset technique. Second, Porter is expected to have a lower error rate or distance than Homer and linear offset technique at all target distances. Third, Porter is expected to have the same performance regardless of target distance. To evaluate the hypothesis, the following statistical methods are used. For the continuous variables, such as time and errors, we used the two-way ANOVA and Tukey's HSD at the 5% significance level. On the other hand, the subjective measurements, which are rated in discrete 7-Likert scale, are analyzed by using Kruskal-Wallis test and Dunes test at the same 5% significant level. We found a significant interaction effect on selection time between technique and target distance. At target distance 3 meters, Homer has a faster selection time than Porter. However, its performance is getting worse with increasing target distance. At 9 meters, Porter is significantly faster than Homer and linear offset technique. These results support our first hypothesis. Porter has no simple effect on target distance, supporting our third hypothesis. A significant interaction effect between technique and target distance is found. Porter shows significantly better accuracy at all the distances, and its performance is not affected by target distance. They support our second and third hypothesis. Next is about throughput. It has a similar result to the selection time. At 3 meters, Homer has the highest throughput, but it is decreased to the lower value by following the distance. Porter shows a consistent result, and it has the highest throughput at 9 meters. The participants rated that Homer caused the least arm fatigue. It shows significant differences from Porter and the linear offset technique. About the self-success and ease of use, no significant differences are found between the techniques in the pairwise comparisons. This is a result for the docking task. The table shows a significant interaction effect on the docking times between technique and target distance. At 3 meters, Porter shows a faster docking time than linear offset and Homer. Porter has a significant difference to linear offset technique, but not Homer. At 6 meters and 9 meters, Porter has significantly faster docking times than Homer and linear offset technique. In addition, Porter has no simple effect of target distance. No simple interaction effect is found. However, in the pairwise comparisons, Porter shows significantly better accuracy at all the distances, and Porter does not have a simple effect on target distance. The same as the selection task, participants rated that Homer caused the least arm fatigue. However, participants evaluate that Porter successfully supports them to dock remote objects and is much easier than Homer and the linear offset technique. The second study is objective to evaluate Porter in comparison to teleportation. It is a 30-minute study, and 22 participants were recruited. We used the same Vive VR device, controllers, and wireless adapter. The same docking task in the first study is used. The independent variables are techniques and target distance. The dependent variables are selection time, docking time, error distance, subjective task load assessment, and virtual reality sickness scores. Here, the selection time indicates the elapsed time when a participant grabs the target first. For the second study, we set three hypotheses. First, Porter is expected to have faster selection time than teleportation because teleportation may require additional movement when the user loses the context of the remote position. Second, Porter and teleportation are expected to have the same docking completion time. Third, Porter and teleportation are expected to have a similar error. No interaction effect between technique and target distance is found. However, the main effect of technique is found, and Porter has significantly better performance than teleportation. Additionally, we found Porter is not affected by target distance, though teleportation does, as the results at 3-meter and 9-meter show. This supports our first hypothesis. We found no interaction effect and main effects for docking time. It supports our second hypothesis. No interaction effect and main effects are found for error distances, supporting our third hypothesis. For all the subjectively evaluated measurements of arm fatigue, self-success, easiness, and motion sickness, Porter and teleportation provide similar user experience. In conclusion, Study 1 shows Porter has better performance than direct Homer and linear offset technique at the further distance for distant object manipulation requiring fine transition and rotation. Study 2 shows Porter allows the participants to manipulate the distant objects as much as near object manipulation. In this work, Porter uses lay casting as its selection tool. We found the participants create Porter for long targets when the target objects are getting smaller by following the increasing target distances. We assume that this is due to the raycasting's known issue called Heinsberg effect, which suffers from the controller's jitter to select small objects. It could be resolved by adopting cone selection. On the other hand, Porter has one advantage of allowing users to interact with objects with both hands free. This enables people to easily utilize uni and bimanual techniques to support simultaneous 6 degrees of freedom plus scale manipulation, such as grab and scale and spindle plus wheel techniques. This is all for our presentation. Thank you for your attention.